SpaceX's Starship Flight 10 has delivered a launch and reentry unlike any before. Flames roared at liftoff, heat shields glowed under immense stress, and for the first time, every single mission objective was achieved. This was not another partial test. It was a complete demonstration of what the world's largest rocket can do. After a history of dramatic setbacks, SpaceX now has proof that its system is working. So, what made this flight different? And why is it such a critical moment for the future of space exploration? And remember, we are building the Planet X community for space enthusiasts like you. Drop your questions below. Some may inspire our future episodes. The launch of Flight 10 began with a display of sheer engineering power. 33 Raptor engines ignited at once, sending the 400-foot rocket and its booster skyward with controlled precision. Spectators on the ground and viewers online saw the fiery exhaust carving into the sky as the super heavy booster lifted clear of the pad. But the real milestone wasn't just leaving the ground. It was how smoothly the entire ascent unfolded. Stage separation, one of the most challenging moments in any launch, was executed flawlessly. The booster detached, performed a flip maneuver, and began its descent path toward the Gulf of Mexico. At the same time, the Starship upper stage, known as Ship 37, fired its engines to continue into orbit. This sequence had failed in earlier flights, where timing or engine issues led to mission-ending problems. Flight 10 showed that these systems are now maturing. The booster itself demonstrated improved reliability by completing its descent and splashing down under control. In earlier flights, boosters were lost due to instability or insufficient control authority. The ability to bring back both major components of the rocket, even in a controlled ocean landing rather than a platform recovery, marks a significant step toward the long-term goal of full reusability. The liftoff and ascent phase revealed the difference between testing and operational progress. Every failure from earlier attempts had provided lessons that were built into this design: stronger valves, improved welds, better engine tuning, and more efficient guidance systems. By Flight 10, those improvements combined to produce a launch that felt not experimental, but deliberate. SpaceX wasn't just managing problems anymore. They were executing a flight plan that worked. Flight 10 carried 4 primary objectives, and all were achieved in a single mission for the first time. The first was an in-space engine reignition. Ship 37 successfully restarted a Raptor engine while in orbit, marking only the second time this has been accomplished with Starship. Reliable reignition is vital for maneuvers in space, whether for adjusting orbit, pushing toward the moon, or initiating a return to Earth. The second objective was to test the payload bay. For the first time, Starship opened its doors and deployed 8 simulated Starlink satellites. These were not operational satellites, but their release proved the mechanism works. Starship is designed to carry massive payloads, from satellite constellations to crewed lunar landers, and this demonstration confirmed that deployment in orbit is now possible. Third, both stages achieved controlled splashdowns. The Super Heavy booster reached its target zone in the Gulf of Mexico, while Starship itself survived reentry and touched down in the Indian Ocean. This dual success is essential for future reusability. SpaceX aims to recover and relaunch both stages repeatedly, reducing costs dramatically compared to single-use rockets. The final and toughest objective came not in space, but in the furnace of Earth's atmosphere. The fourth milestone was testing the heat shield. The new thermal protection tiles had to endure re-entry at extreme speeds and temperatures. Unlike earlier tests, where tiles were lost and exposed steel burned, Flight 10 proved that the system is advancing toward operational reliability. Each of these achievements represented a first. Together, they marked the transition of Starship from experimental hardware to a spacecraft capable of performing all the tasks expected of it. Reentry was the most dramatic and critical phase of Flight 10. As Ship 37 plunged back toward Earth, onboard and tracking cameras captured the vehicle glowing as plasma formed around its surface. The temperatures reached over 1,500 degrees Celsius, putting every component of the heat shield under maximum stress. The protective system is made of thousands of black ceramic hexagonal tiles designed to absorb and deflect heat. Previous flights had exposed weaknesses, some tiles detached, others cracked, and damage accumulated in critical areas. Flight 10 told a different story. The shield held. Reports indicated only minor damage to certain surfaces and flaps, but overall, the system remained intact. This isn't just about surviving re-entry. It's about proving the technology needed for reusability and crew safety. A reusable rocket must be able to fly again without extensive rebuilds. For human missions, astronauts returning from the Moon or Mars must rely on shields that work every time.